Hi, this recording is for AP Chemistry and it is on equilibrium and the basics of finding K and the equilibrium constant. Let's start by looking at what is equilibrium. Equilibrium means that the forward reaction and the reverse reaction are proceeding at the same rate. So you have a net gain of nothing. You are making the products as equally as fast as you're making the reactants. And one of the characteristics of an equilibrium reaction is this double-headed arrow here, where it is saying that you are making C plus D as fast as you are making A plus B. There are cases where an equilibrium does favor one side or the other, and those are going to be the factors that we look at throughout this chapter. For right now, we're just going to focus on what is equilibrium and what are some of the numbers associated with finding it. Here's an example, the Haber process. A German chemist found a reaction that was able to make ammonia, NH3, but the reaction also broke down, forming nitrogen gas and hydrogen gas. That's one of the most common ones that you see as an example of equilibrium. So equilibrium often, like I said, can go forward and reverse. Well, it is forward and reverse, but sometimes there is a value that indicates whether you are making the reactants or the products. And that value is, we're going to change color. The value is K. So what we're going to spend the majority of our time on in this chapter is determining K, which is the equilibrium constant. So we are going to be learning lots of different ways of using K and finding K. Now this K is different than the kinetics K. This K is a capital K, and it will most often have a subscript. You can see that you have a subscript of C whenever we're dealing with concentration, which would be in molarity, and you can have a P whenever you're dealing with pressure, and that usually is ATM or kPa. Okay. K with the subscript of EQ as it's shown here is just saying it's an equilibrium constant. Finding K, equilibrium constants, are really quite simple. The process is called the law of mass action, and what it's saying is the relationship between the reactants and the product's concentrations. And when you do a K value, you will use the coefficients in a reaction. Now, if you think back to kinetics, in kinetics the coefficients did not matter, but in this case, the coefficients are the critical factors. So I'm going to go ahead and underline the coefficients here. And I chose to use letters to help us understand. But what happens when you're doing equilibrium value that you're calculating? You take the products over the reactants, and you're going to raise the product to the coefficient, and you're going to raise the reactant to its coefficient. So as you can see in the screen here, you can see that E raised to the E power, so its coefficient, times F's concentration raised to the F's constant, the whole thing divided by A raised to the A constant and B raised to the B constant. So it can be numbers, but most often you're going to see it as a generic form for the equilibrium constant. Kc will only depend on the coefficients, the stoichiometry of the reaction. We're not worried about the mechanism or how many steps it took care of, and K does vary with temperature. So you're going to have different equilibrium constants at different temperatures. So let's take a look at what finding an equilibrium constant actually looks like. Here's an equation where we have K is, we're trying to find the Kc for this equation, N2O4, and makes 2NO2. So to find the K value, you take the products over the reactants. So in this case, we're going to have NO2 raised to the second, because that's the coefficient, divided by N2O4. Now, if they gave us values for NO2 and N2O4, as we're given here on this second line, we can plug those numbers in and we can actually find a value for our K. We plug them in, we square the one value, divide the whole thing, and you get a K value of 0.211. There are no units when we're finding equilibriums K. That's another change from kinetics. In this case, there are no units. We have concentration over concentration, so they cancel. There's no units. We don't have to worry about what the order or how many we're raising it to. It is straight up just K. Now, the value of K has some meanings, and we're going to be looking at that in the next couple of lessons. There are a couple of rules for finding equilibrium constant. For the constant, remember, there are no units, and two things can change the constant. You will have a different constant if you have a temperature change or you have a different reaction. Okay, so you could be looking at a specific reaction at two different temperatures and you will have two totally different equilibrium constants. Like I said, this is pretty simple. Try not to get your K's confused. This is a capital K. You're going to take the products divided by the reactants, and the coefficients in the balanced chemical equation does matter.